Hey there. Let's take a look at some additional modular exponentiation examples. This time we're going to be working in Z13. I'm including the table this time just so we can look at some stuff in it, but one of the things that you want to think about while you're doing these problems is how would you do it without the table. Obviously, Z13 is small enough that we can include the table, and it's not too hard. And worst comes to worst, it's always something to go back to if you ever get stuck. But if we were working in like mod 473, we're not going to make a table. So just kind of keep that in mind as well. So first one we're going to look at is find four natural numbers, m, such that 2 bar m to the m equals 1 bar. And just, I'm going to stop saying the bars. I'll write them in, but just so we know that, I'm just not going to say them every time. So what do these exponents have in common? So, well, let's think about this. We do know that according to little Fermat, that clearly if we're in mod 13, then we know that 2 to the 13th, I'm sorry, just kidding, 2 to the 12th equals 1. Because mod 13, prime number, so all of the values there are relatively prime to it. So little Fermat guarantees us that z or 2 to the 12th will be 1. Okay. So the question is, what other four natural numbers out there? Well, there's an easy one. We could say 2 to the 0. And some will argue that 0 is not a natural number. I'm fairly certain your book doesn't include it. That's kind of an open question at the moment. I think we're slowly moving towards adding 0 to the natural numbers. It's not a big deal at this point. I'm going to include it there. Turns out it's not going to need it because we need 2 more. Well, what's happening? We know that as we looked at this chart from before, as we go through 2, we certainly get down to the 1 here. And what happens? Well, the k equals 13 row is really the same thing as the k equals 1 row. K equals 14 is the same as the k equals 2 row, and so on. So what really happens is we can take a look at z to the 20, not z, I don't know why I keep thinking z, because my 2's look like z's. 2 to the 24, we can certainly write that as 2 to the 12th times 2 to the 12th. But since we know both of those numbers are 1, that means this whole thing is just going to end up being 1. Okay? And so then I could also say 2 to the 36th by the same reasoning, 2 to the 48th, and so on. So basically, what we're saying is that all we're looking for powers of m is that they're multiples of 12. Okay, they're multiples of 12, or another way to say it is that they're 0 mod 12. Okay, so keep in mind, we're working in Z13, but these exponents repeat on a modular system 1 less than the 13. So that's why we're seeing the 12. And so if I look at the next one, what about if I want to find out where 2 values of natural numbers of m where 2 to the m equals 2? Well, looking at my table again, I notice, clearly it's happening here at 13, and that means it's happened at 1 as well. So 2 to the 1st is going to be 2. 2 to the 13th is 2. And because we know the way these repeat each other, the other values we can look at are going to be 25, because I'm going to see those values repeat every 12, 37, 49, so on. So what we notice here, there's a lot of ways we can describe this, but probably the most sophisticated way to do that is we notice that these are the congruence class of 1 mod 12. Okay? In other words, they have a remainder when divided by 12. So notice this relationship between the mod of the system we're working in, Z13, and the powers. when we're looking at raising it to an exponent. Okay. Another question we might ask is find 4 natural numbers. Let's see. M such that 2 to the m equals 4. And again, we can see just if we look at our table, clearly the first place that this shows up is right here at 2 squared. And so I'm going to go ahead and claim that m equals 2. And then 12 more than that would be 14, and then 26, and 38, dot, dot, dot. Or another way to say it is that m is 2 in mod 12. Now, one other thing, just kind of an aside that I'm going to mention is that I also claim, and this is if we go outside the natural numbers, I'm going to also claim that m equals -10 works as well, which is kind of interesting when you think about it, because we often think of negative exponents to mean something different when we're working in the rational numbers. But in congruence classes, if -10 and 2 are in the same congruence class, mod 12 stands to reason. But that's something for later. Okay. Now, I want to do, so these first 4 are pretty straightforward. Let's see, I'm going to add another version of my mod 13. Sorry for that. Okay, so here's another version of my mod 13 table, so I didn't have to pull the other one down. So I'm going to, let's say, consider a slightly different question. Okay, so this is kind of a contrast to it. So what if I want to find 4 natural numbers m such that 3 to the m equals 1. This is where things get a little more interesting, because notice what happens. When we look at our table over here, we've got 3, so 3 to the first is 3, 3 squared is 9, that makes sense, it's not overlapping. But then we go 3 to the third is 27, or 9 times 3 is 27, but in mod 13 that's 1. So it turns out we have that 3 to the third power is equal to 1, which is kind of interesting. And in fact, we see that it shows up here is k equals 3. It also shows up in 6, and it shows up in 9 before it gets back to 12. So kind of interesting. So unlike little Fermat guarantees that 3 to the 12th is going to equal 1. But it doesn't preclude other values doing the same thing. Okay? So that's what's kind of interesting here. So we see that our m values, and I'm going to use 0 too, because obviously 3 to the 0, again, we'll use our natural numbers. So 0, 3, 6, 9, 12, 15, so on and so forth. Notice that it repeats with a period of 3. Okay? And even though little Fermat guarantees 12, 3 divides 12. And that's kind of important. And the reason why is that this has to sync up at 12 again. Okay, in order for little Fermat to be true, and all of the numbers in mod in Z13 when raised to the 12th power should equal 1. So if I'm going to have something else that's repeating more frequently than that, it has to still repeat on a period that is going to sync up when we get to 12. And so you'll notice that, like, obviously in 3 and in 9, they repeat at 3, 6, 9, and then 12. But then when we look at 5 here happens at 4, happens at 8 before it returns at 12. And the same thing is true for 8. 8 happens at 4, 8, and 12. And then there's a couple that happen every 6. 4 and 6 and 12. And then also 10, 10 to the 6th and 10 to the 12th. And then 12 being somewhat unusual, every second one. But we knew why, because remember that's alternating between positive and negative 1, because 12 is essentially negative 1 in mod 13. So it makes sense that that's going to alternate back and forth. So you'll notice that these repeat themselves. At no point is there anything in the row for 5, because if a 1 appeared in this row, row 5, there's no way for it to sync up again when it gets to 12. So in other words, if for some reason our period was 5 and we went from 5 to 10, it's not gonna sync back at 12. So any period that's less than 12 is going to have to be a divisor of 12. Okay, so it's really an interesting way to think about that, and just well, yeah. Okay, so in general, what we would say. So let's move that up one more time. In general, the repetition has to repeat with a period that divides the original mod minus 1. Okay? And as with many of the things that we talk about in here, this can get much more sophisticated down the road. So, but this is a good place to start. Or, as it were, end this video for now.